Hello, this is Ms. Suger. Welcome to Lesson 6.4, Cut by a Transversal. Our essential question for the day is, how can I prove the following theorem, which states, a line parallel to one side of a triangle divides the other two proportionally. Here's an example. Let's say I have a triangle, we'll call it ABC, and I add in a line, we'll call it YZ. I know that YZ is parallel to BC, marked here. What I've actually done here is created two triangles that are similar, meaning they have congruent angles and proportional side lengths. To make this a little bit easier to see, I've made triangle ABC blue and triangle AYZ purple. Alright, let's review corresponding angles. Here we have two parallel lines noted in black and a green line that cuts through them. This green line is called a transversal. The neat thing about this is that it doesn't matter how the transversal cuts these parallel lines, the results will always be the same. You can see we have four angles on both the top and bottom line. I've gone ahead and labeled the top 1, 2, 3, and 4. Now, whatever measure for angle 1 at the top is, will also be the measure for angle 1 at the bottom. Similarly for 2, 3, and 4. This is because corresponding angles of parallel lines cut by a transversal are congruent. And with that, we can get back to our triangle ABC. I went ahead and labeled point Y with angles 1, 2, 3, and 4, along with the corresponding angles 1 and 2 on point B. I have also put an angle 5 on the other side to show that angle AZY is congruent to angle ACB. So we can now list out in bullet points starting with what was given. Line segment BC is parallel to YZ. Then angle ABC is congruent to angle AYZ, which we can see by angle 2. Similarly, angle ACB is congruent to angle AZY, shown by angle 5. Again, these are called corresponding angles. Our goal is to use this information to show that triangle ABC is similar to triangle AYZ. So let's go ahead and jump into that two-column proof. Alright, hopefully this is looking familiar to all of you. We're going to have our statements on the left-hand side and our reasons on the right. As always, we start off with our given information. In this case, line segment BC is parallel to line segment YZ. Next, we can use the fact that corresponding angles are congruent to state that angle ABC is congruent to angle AYZ and that angle ACB is congruent to angle AZY. This next line is not necessary, however I think it's good to point out that since the two triangles share an angle at point A, angle BAC is congruent to angle YAZ, or in other words, all angles are congruent to themselves. The reason I say that we don't need that last point is because the similarity postulate is only angle-angle, not angle-angle-angle. Recall that the interior sum of angles in a triangle is always 180. Thus, if you know that two of the three in both are the same, it must be the case that the third is the same as well. And I'd like to note that AAA is not a rule for congruence. One way you can prove this to yourself easily is to think about equilateral triangles. They always have all their angles equal to 60 degrees, but they can have any value for the side lengths. So I could have an equilateral triangle with all the side lengths of 3, and I can have another equilateral triangle. Still, the angles are all the same, but now my side lengths are 15, and since 3 doesn't equal 15, the two triangles are not congruent. Okay, so question for you. Does side length YB divided by side length AY equal side length ZC divided by side length AZ? Take a moment to yourself to think about this. Alright, if you need more time, go ahead and click that pause button. But if not, I'm going to go ahead and tell you that the answer is yes. You should have learned that from the task that you completed earlier today. We'll go ahead and prove this, but first I want to do a quick algebra review. I'd like to go over expanding fractions. A plus B all divided by C can be expanded to A divided by C plus B divided by C. An example of this is 2 plus 5 all divided by 6, which can be expanded to 2 sixths plus 5 sixths. Only now can we reduce it to 1/3 plus 5/6. you cannot, I repeat, you cannot say that it is equal to 1 plus 5 all divided by 6. You can check that by saying, well, 2 plus 5 divided by 6 is the same as 7/6, whereas 1 plus 5 divided by 6 is 6/6, or 1, and 7/6 is not equal to 1. So again, yes, do this, don't do this. And with that out of the way, on to our proof. Once again, we have our 2-column proof with statements on one side and reasons on the other. Just as before, we are going to start with our given, which is triangle ABC is similar to triangle AYZ. From this, we can use our definition of similar triangles to say that a common ratio exists. More specifically, we can write this as side length AB divided by side length AY is equal to side length AC divided by side length AZ, which is also equal to side length BC divided by side length YZ. From the diagram, we can see that side length AB is just combining side length AY and YB, since line segment YZ cuts triangle ABC. Similarly, line segment AC is going to be combining sides AZ and ZC. Now I can use substitution to plug step 3 into the bolded parts of step 2 and get AY plus YB all divided by AY is equal to AZ plus ZC all divided by AZ. We can now put that algebra review to good use by expanding this equation to AY divided by AY plus YB divided by AY equals AZ divided by AZ plus ZC divided by AZ. Whew. Sorry about all those letters, but hopefully that makes sense to you guys. We also know that anything divided by itself is 1, so this can be simplified to 1 plus YB divided by AY is equal to 1 plus ZC divided by AZ. And finally, we can subtract 1 from both sides to prove that YB over AY is equal to ZC divided by AZ. And with that, hooray, we're done! Insert all 3 of the celebratory clip art photos PowerPoint has. If you'd like, go ahead and stop here. But if you'd like some more review, I came up with 3 pretty good homework problems, I think. Completely optional, you do not have to do them. But if you like, you can go ahead and go to the next slides to see it. So, question 1 is, let's say that I still have my triangle ABC, but extend the lines a little bit and create line segment DE, which is parallel to side BC. Go ahead and try and write 3 equal ratios involving D and E, and then prove one of them. An example of this would be AD divided by AB plus AE divided by AC. This should look very familiar to the stuff we did with YZ. Our next question would be if I had line segment FG that was parallel to side AB. Here, you should write 2 equal ratios involving F and G and prove one of them. And finally, for a little review of the Pythagorean theorem, which is a squared plus b squared equals c squared. If you'd like to see the fun fact of the day, look down in the description, it relates to this. Alright, so given the 2 similar right triangles below, the first of which has a base of 6 and a hypotenuse of the square root of 37, and the other with a base of 12, height of x, and hypotenuse of y. Is it possible to find the values of x and y, and if so, what are they? Alright guys, that's all I've got for this video today. I'm still in class until Thursday and can answer any questions in class. I'm not sure how long my current email is going to stay active after I leave, so I went ahead and created a new one. It's misszugersclass@gmail.com. Note that there's a period between the S and the Z. I'm going to put the optional homework solutions in the next video, so please put any questions you have in the comments down below. Someone else may be wondering the exact same thing. I'm going to try and make a Q&A video using those questions along with some of the more common ones that you've emailed me before your next big unit test. And with that, thanks for watching. See you soon. Bye!